All right, everyone, we're really happy to have Alex Wein today speaking about low degree hardness of random optimization problems. This is in my opinion, very exciting recent work trying to establish low degree polynomials as a source of hardness for optimization as well as hypothesis testing. Anyway, really happy to have Alex. Alex, take it away.
Great. Yeah, thanks a lot. And thanks to all the organizers for having me. So this is joint work with David Gamarnik and Akosh Jagannath. And so just to sort of set the stage, I'm going to be talking about random optimization problems. So optimizing some kind of a random function in high dimensions. So there are some discrete variants of this. For example, finding a maximum clique in the random graph. Right, so suppose I give you some random graph, maybe an Erdős-Renyi graph. Your goal is to find the biggest clique that you can. So a clique being a fully connected subgraph like the one shown in red here. Another example along the same lines could be max k-sat on a random formula. So I give you some random k-sat formula, and you need to find an assignment that satisfies as many clauses as you can. Another example of a more continuous nature is maximizing a random polynomial. So imagine I give you a polynomial in n variables with random coefficients, and you need to find a point on the unit sphere that achieves as large a value as possible. Note that these are different from some of the other types of problems that are sometimes considered in that there's no planted solution. So sometimes you consider planted clique or something where there's a planted solution and the goal is to find that one. Here, we're just given random data and the goal is to find a certain structure that's sort of naturally occurring in the noise. And so there's a few natural questions to ask here. The first one is just for a typical random instance, what is the optimum value? So I give you a random graph. How big is the actual biggest clique in that graph? But of more relevant to the algorithmic question, we'd like to know what objective value can you reach with a polynomial time algorithm. So I'm going to write opt for the actual optimum value and write alg for the best possible value that we can achieve with known polynomial time algorithms. And so we'll see that sometimes these problems seem to have computational hardness. So there will be some cases where it seems computationally hard to reach a particular objective value. And in these cases, we'd like to understand why it's hard. And furthermore, we kind of like to understand this in a unified way that explains, all of these examples I've written here plus more, sort of with a unified explanation instead of some kind of ad hoc explanation that applies separately to each problem. Okay, so here's a more concrete example now. The maximum independent set problem. So suppose I give you a sparse Erdős-Renyi graph. So just to clear up the notation, n is a number of vertices. And this d over n is like the edge probability. Right, so each of the n choose 2 possible edges occurs with probability d over n, and I'm going to imagine d being a constant here. Right, so this is so d is the average degree of the graph, and we're going to take this to be a constant. Okay, and so the goal is to find the largest independent set that you can find, an independent set being a subset of the vertices that has no edge within it. So no edge that has both endpoints in the set. Okay, so what do we know about this problem? The actual optimum value is known to be, a particular constant or particular value. But the best known algorithms only achieve something half as good. And this is by a greedy algorithm. So a very simple algorithm achieves, finds an independent set that's half as big as the biggest possible one.
Alex, I think I can't hear anything. So I think we lost your mic. No. Oh, maybe no.
Try without the headset. Can you hear me now?
Yeah. Now we can hear you.
Okay, sorry about that.
Okay.
All right, so so in the maximum independent set problem, right, the actual biggest set is this size, but algorithmically we only know how to find one of this size. And so some structural evidence has started to emerge that suggests that maybe it's impossible to improve this algorithm. And roughly speaking, the structural evidence says that if you look at sets of size larger than alg, they sort of separate into different clusters. And they do so in a way that suggests that maybe some kind of local or Monte Carlo method cannot easily traverse this landscape. Now, a more concrete result along these lines, that's now sort of the state of the art, is that a class of algorithms called local algorithms can achieve the value alg, but no better. Okay, so this is some restricted class of algorithms for which alg really is the fundamental limit. And what is a local algorithm? I'll tell you briefly. So remember, we have sort of a sparse random graph where each vertex has a constant number of neighbors on average. A local algorithm just means that each vertex gets to look at some constant radius which will look like a tree. And within that radius, it gets to make a decision about whether it should be in the independent set or not. And what it gets to use is the topology of the tree, but also these random IID variables attached to each node. So for each node, there's sort of a variable x sub v for vertex v. And these are, say, just going to be IID from some distribution, maybe uniform on 0, 1. It's not terribly important. Right, so a very simple algorithm you can implement in this way is what's called taking all the local maxima. So each vertex puts itself in the independent set if it has the largest label among all of its neighbors. Right, and you can see that this will be an independent set in the graph. Okay, another example that I want to talk about because it's of a slightly different continuous nature is what's called the spherical p-spin model. So this is a problem where the input is a random tensor, right? So tensor being here like an n by n by n by n grid full of random Gaussians, where p is the number of dimensions there. And the goal is just to find a unit vector that sort of maximizes this, this tensor form. And so what's known about this is that the optimum value is some constant under this scaling, but the best known algorithms achieve some different constant. I won't try to get into what the constants are, but the algorithmic threshold is smaller than the true optimum, as long as p is greater than 3. Notice that for p equals 2, this is just an eigenvalue problem. So we're just given a random matrix and you want to find, maximize v transpose yv. And this, of course, we can do in polynomial time. But for p greater than 3, this is like a highly non-convex function that's not clear how to optimize. And what's known in this setting is that this class of algorithms called approximate message passing achieve the value alg and no better. Right, so this again is some restricted class of algorithms for which this conjectured value alg is truly the fundamental limit. And roughly speaking, what are approximate message passing algorithms? Well, they get to do a couple of different operations, but one of the main ones is what's called tensor power iteration, which just means, I'll write out the formula here. Okay, so, right, so this is sort of a natural way to take in some vector and sort of hit it against your tensor to get out another vector. This is sort of, think of it as some kind of gradient descent. So it gets to do this along with some kind of entry-wise transformations. So updating V to some, entry-wise function of itself. And it also gets to kind of take linear combinations of its past states and things like this. Okay, so I won't try to define formally the exact class of algorithms, but this AMP is a fairly powerful class of algorithms that's achieved state-of-the-art results for all kinds of problems. Okay, so right, it looks like I've shown some pretty nice results for both of these problems already. So what's missing? So, right, on a philosophical level, we'd like to have a way to give the best possible evidence that there are no better algorithms. Now, we can't really hope to really prove this definitively, like prove that no polynomial time algorithm exists, even assuming something like P not equal NP. This is just beyond the reach of current complexity theory. But we'd like to still have some kind of framework for when we think things are easy versus hard. And so, right, what does the prior work do? It rules out certain classes of algorithms. But we should kind of ask ourselves, do we really expect these to be the best types of algorithms that we know how to do? And in particular, one thing that's concerning is that this AMP algorithm I told you about is actually not optimal for a slightly different problem. So tensor PCA, you can think of this as being similar to this p-spin problem I talked about before, except that it has a planted signal now. So now there's like actually a planted rank 1 signal plus Gaussian noise. Right, so it's very much analogous to the other problem. But for here, interestingly, this AMP is not the best algorithm you can do. The best algorithms are certain spectral methods that involve reshaping the tensor in a slightly different way. This so-called tensor unfolding. So for instance, building a matrix, just if you have a 4 tensor, you can flatten it to a matrix in sort of the obvious way and then take the top eigenvector of that. So this will work, but the tensor power iteration type of methods, including AMP, do not work. So that's one concern. We would also like sort of a unified framework that applies to all problems. And so I talked about these local algorithms, but these local algorithms are quite specific to sparse graphs. And so we couldn't use local algorithms to, say, explain the p-spin problem. And so the solution that we kind of propose in this work is to prove lower bounds against a larger class of algorithms that contains both local algorithms and AMP algorithms and all sorts of other things. It also includes the optimal algorithms for tensor PCA. And these algorithms are called low-degree polynomials. Okay, so what is this low-degree framework? We want to study the power of a certain class of algorithms called low-degree polynomials. So what do I mean for a polynomial to be an algorithm? Well, I'm considering a multivariate polynomial. By this, I just mean that, you can really think of it as a tuple of different polynomials where each one of them is just a usual multivariate polynomial in m variables. And we think of the input of this polynomial as just being whatever input we're given in the problem. So for instance, it could be a random graph represented as its adjacency matrix. And depending on the setting, the output will be, whatever constitutes a solution to our problem. So if we're trying to do a decision problem, maybe we just want to output a single bit, whereas in our cases, we will want to output some vector, which maybe is like the indicator vector for the position of the large independent set. And I've been saying low degree. Low degree is going to mean roughly logarithmic in the dimension, and I'll justify why that's sort of the interesting choice a little bit later. But it's important to note that a lot of the state-of-the-art algorithms that are used for these types of problems can be captured by this framework. So if we imagine that the input is a matrix n by n, one of the most basic things I can capture using low-degree polynomials is just power iteration. So let's say I start with the all ones vector, and I just multiply this by my matrix a bunch of times. And this will give kind of an approximation to the top eigenvector of the matrix, which is itself a polynomial of degree k. These AMP algorithms that I talked about earlier are also low-degree polynomials. And in fact, they are degree constant, because typically you need a constant number of iterations of this AMP, and each iteration can be well approximated by a constant degree polynomial. And also these local algorithms on sparse graphs that I talked about before, if the radius that each vertex is allowed to look at is constant, then these also can be thought of as constant degree polynomials, or at least well approximated by constant degree polynomials. And the reason is basically that each vertex only has a constant number of nodes in its neighborhood. And so you can sort of brute force enumerate over the possible neighborhoods of any given vertex. So if L is the number of nodes that other nodes in the neighborhood of a vertex, you need a polynomial of roughly L to sort of check all the possibilities. Essentially, you're not just limited to these types of things. You can also do kind of any pre-transformation you like to your data. Typically, we think of like a constant degree transformation. So you take whatever data you're given, you build maybe some other matrix, and then do power iteration on that. So this captures all sorts of non-trivial spectral methods like tensor unfolding, like the non-backtracking walk matrix used in community detection, and all sorts of other things. So I hope this illustrates that this class of low-degree algorithms is fairly broad and captures a lot of the things we may want to do. And so, okay, to motivate further why maybe these low-degree algorithms are a good idea. Well, for problems with a planted signal, this low-degree framework has actually already been quite well established. So low-degree polynomials have been sort of studied as an algorithm and shown to basically be the most powerful things we know how to do for a lot of problems. I'll say this more specifically soon. But this comes really from this very excellent line of work in the sum of squares hierarchy, which first motivated looking at these low-degree polynomials as sort of a proxy for computational hardness. And so to illustrate more concretely what I mean by a planted problem, the maybe most canonical example is the planted clique problem, where you have a random graph, g n 1/2. So each potential edge occurs with probability 1/2. But then you plant a clique. You kind of add a clique, like the one shown in red, of size on k vertices. And in these types of settings, you ask usually these two different questions, detection and recovery. Detection is just about whether you can tell if there is a planted clique at all, or in other words, whether you can distinguish between a purely random graph versus a graph that has a planted clique. And then on the other hand, recovery is the problem of actually finding the clique. And for both the detection and recovery problems here, there's sort of a well-known, statistical to computational gap, where when the clique is too small, it's simply impossible to find it in this region. If the clique has a size exceeding root n, we know there are simple spectral methods and so on that can find it. But in the middle, there's this sort of hard regime where you could find the clique if you're allowed to brute force search over all of them, but we don't know any polynomial time algorithm to find it.
Oh, Alex, I have a question. So,
yeah.
Can you maybe describe again what the computational model is? So an algorithm gets to pick a fixed collection of polynomials, and you evaluate all these polynomials and make your decision based on that?
Yeah, so the algorithm itself is this polynomial from r to the m to r to the n, or you can think of this one polynomial as really a tuple of polynomials, one for each output. Yeah, so that is the algorithm. It is just this one fixed polynomial, and then when some instance comes along, we give you, say, a graph or something, you just plug this into the polynomial, and that gives you the output. So you can think of the output here as being an indicator vector that tells you the position of the clique.
Don't you need randomness?
Randomness in, yeah, so often turns out you don't, but yeah, you can consider a random polynomial as well. This basically won't change any of the results if you consider a polynomial that's allowed to itself have random coefficients. But in a lot of these cases, we can actually show that randomness is not needed. Like the best low-degree polynomial is actually just a deterministic one. Good. Any other questions about the model? Okay, so in the setting of planted problems, it's sort of already been established that for a big list of all of our favorite problems in high-dimensional statistics that have some kind of planted structure, that it is the case that the best known polynomial time algorithms are actually captured by these log-degree polynomials. And well, one reason for this is basically because the best known algorithms tend to either be some kind of spectral method or some kind of approximate message passing. And sort of the reason for this log n is kind of because of these spectral methods. So typically you have a spectral method where the top eigenvector tells you something about the truth, and you also typically have kind of a spectral gap between the first two eigenvalues. And because of this, you need log n rounds of power iteration to approximate the top eigenvector or top eigenvalue. And so that's sort of where you can think of this log n as coming from. And so on the flip side, we're also able to show that low-degree polynomials fail in this conjectured hard regime, right? So this gives quite a nice, general explanation of what makes these problems hard versus easy, right? If a new problem comes along, you can analyze how well do low-degree polynomials solve this problem. If they succeed, then this suggests there should be an algorithm, say a spectral or AMP algorithm. And if they fail, then this gives, fairly compelling evidence that maybe there is no algorithm for this problem. Or at least any algorithm for this problem would need to look a bit different from the types of things we usually use, like spectral and AMP. And so the point of this current work is to see if we can extend this framework to this non-planted setting, whether these computational hardness of non-planted problems can also be explained by low-degree polynomials in the same way. I should mention, of course, that there are some other frameworks for trying to understand these types of computational hardness. This includes the sum of squares hierarchy or the statistical query model, which have also had a lot of successes. But these, it does not seem so clear how to apply them to the non-planted optimization problems that I want to talk about. For sum of squares is really solving what's called the certification problem instead of the optimization problem. So it's not so clear how to use sum of squares methods to solve these non-planted problems. And statistical query model is sort of restricted to cases where you have IID samples from some distribution, which is also not really the setting that you're looking at here. One caveat of this framework that I should perhaps mention, there are some cases where there are some limitations to this approach. So one kind of common counterexample is the Gaussian elimination algorithm. So if you're given some XOR equations and you want to know if they're satisfiable, you can use Gaussian elimination to exactly compute whether or not they are satisfiable. But this is not a low-degree polynomial, and low-degree polynomials, fail at this problem. But somehow this is like a very brittle algebraic structure that we're exploiting with this algorithm. And for instance, if I only want to know if I can satisfy 99% of the constraints, then Gaussian elimination no longer works. And so, these low-degree polynomials maybe seem to be measuring more of a robust notion of hardness. So if we restrict ourselves to problems where maybe a small fraction of the coordinates have been corrupted or something like this, then low-degree polynomials seem to really match the best known algorithms for all of these types of high-dimensional statistical problems. All right, so I hope I've sort of convinced you that low-degree polynomials are an interesting class of methods to look at. Are there other questions at this point? So let me now tell you what we can actually prove. So let's first think about this spherical p-spin model. So this is like optimizing a random polynomial on the sphere. And if you remember, there were these two separate thresholds. The best known algorithms achieve some constant, but their true optimum value is a different constant. And what we can show is that no low-degree polynomial can get all the way to the optimum. Right, so we sort of have opt value. The best known algorithms only get up to here. Here's sort of 0. And we're showing that there's at least, there's some region here that is hard for low-degree polynomials. And so to more formally state this, I need to sort of define what exactly does it mean for a low-degree polynomial to optimize this function. So these two bullet points kind of define what it means to succeed. So this objective function, I'm going to call h of v. Right, this is the thing you want to maximize. And so for a polynomial to succeed, we'd like these two criteria. First of all, the objective value applied to the polynomial's output needs to be good, right? So remember, this is a polynomial that takes in the whole tensor, the whole y, this input, and it's trying to output this vector v, right? Or it's trying to output a good solution v. And so you want v to achieve a good value, and you also want v to be normalized correctly as required by the problem. Okay, so these 2 bullet points sort of define what it means for a polynomial to succeed, and what's the theorem saying. Okay, this is, for technical reasons, restricted to p being 4, at least 4, and also even. But what it's saying is there's some epsilon where no low-degree polynomial can succeed at getting to value op to minus epsilon. Here we're taking polylog as sort of the polynomial degree, just to be safe. But one caveat of the result is that we do need to assume this explicit error probability on the algorithm. So, ideally, the ideal theorem would perhaps just have a little o of 1 here instead of this explicit bound, but we instead have, an explicit failure probability for the algorithm. But somehow this is not too serious, because the types of algorithms that succeed in this easy regime that can say get up to the value alg, the best known existing algorithms, will have a much better failure probability than this, essentially e to the minus n. And so this failure probability is somewhat reasonable. Okay. And let me show you the similar result for maximum independent sets. So here, if you remember, the optimum value was something, and the algorithmic value was half of that. Right, we can show that some threshold, which is roughly 1.7, that again there's some hard threshold that the low degree algorithms cannot pass. Right, so the theorem statement is similar to before. It's a bit more technical, because what does it mean for a low degree polynomial to output an independent set? Well, basically we ask for it to output a value close to 0 on each index that's not in the set, and to output a value close to 1 for each index that is supposed to be in the set. But we sort of relax the conditions a little bit. It's just for vertices not in the set, it's supposed to output a small value. For vertices in the set, it's supposed to output a big value. And it's also allowed to, screw up on a small number of coordinates and output something else, say like a little O1 fraction of coordinates. And what you want is that if you then take all the indices corresponding to the large values, you want this to almost be an independent set of the right size. So I say almost because we again allow it to make a small number of mistakes, which we just sort of throw out. And sort of, right, you may worry that this is not really the optimal threshold, but in upcoming work, it's actually possible to improve this to the optimal threshold. Right, so now we can really prove that this value alg is achievable by low degree polynomials, and also that low degree polynomials cannot achieve anything larger than this. All right, any questions about this before I sort of tell you how to prove such a thing? Okay, so how do we prove failure of low degree polynomials? So it's already been well established that for problems with a planted signal, there are methods to do this. And in these cases, it actually boils down to a fairly simple linear algebra computation. So you can somehow directly, write out a criterion for polynomials to exist, and it just boils down to a linear algebra problem. Specifically for detection, it turns out you need to take some kind of likelihood ratio and project it onto the space of low degree polynomials. So these are sort of, straightforward, explicit calculations that you can do. Whereas for random optimization problems, it does not seem that these types of techniques work. And so we instead will use this indirect approach. So it has two parts. The first ingredient of the proof is going to be stability of low-degree polynomials. So low-degree polynomials somehow have this property that when you perturb the input a little bit, the output should not change too much in sort of an average case way. And then we're going to use some kind of structural property of the solution space. So this is called the overlap gap property. More accurately, we're using some variant of the overlap gap property. There's been lots of different variants of OGP used for different purposes. But the version we're using here is most directly inspired by this line of work. And particularly this last paper essentially uses the same variant of this OGP. And so this OGP, I'll tell you what it means in a second, but it's some property that rules out the success of any stable algorithm. And so combining these 2 points gives you the result. So let me now talk about those two ingredients of the proof sort of separately. The first one is this fact that low-degree polynomials are stable. So what do exactly I mean by this? Well, let's imagine that y and y prime are two Gaussian vectors that are row correlated. So row correlated just means that the covariance between the two of them is row times the identity. Okay, so these are m-dimensional vectors. And for our purposes, we're going to imagine this row being pretty close to 1. So they're actually very well correlated. So you can think of y prime as just a small perturbation of y. And let's take one of these low-degree polynomials that maps y to some other space. And for normalization purposes, we'll say that y outputs something that's basically norm 1 on average. And so here now is the result. So what is it saying? I mean, sort of a tail bound saying that, if I look at f's output on y versus f's output on y prime, then most of the time, then like with pretty high probability, this needs to be small. So remember, I'm taking p equals 1, or p close to 1. And so this is going to be some very small value. Right, so this is sort of a sense in which low-degree polynomials do not change their output too much when the input is changed, so long as this change is sort of in a random way. Okay, how to prove such a thing? It sort of follows from basic known facts about low-degree polynomials. So if you've ever looked at this book by Ryan O'Donnell, which I highly recommend, you'll know that low-degree polynomials have properties like low noise sensitivity, low total influence, and something called hypercontractivity, which kind of means that the moments are well behaved. And combining these ingredients gives you this type of result. But I won't go into too many more details of this. But let me instead talk about what the analogy of this should be for the Boolean case, right? So that result I just told you about will be used for the p-spin model where the input is Gaussian. But what about if we want to do this independent set problem, where now the input is, it's an Erdős-Renyi random graph. So it's basically IID Bernoulli, right? So in what sense are low-degree polynomials of these types of variables stable? So for here, I want to think about what's called the interpolation path. So the first one, so I'm going to draw a bunch of these different Bernoulli random vectors. The first one is just drawn IID Bernoulli. But then at each step, we're going to resample one edge, or resample one coordinate. Each coordinate corresponds to an edge if I'm thinking of it as an Erdős-Renyi graph. So the first step, I will, resample y1, the first coordinate. And then at the next step, I'm going to resample y2, and so on. And so there's m different coordinates, and so each one gets resampled once, just in some fixed but arbitrary order. Okay, so I start with some random vector, and I resample the coordinates one by one. And now I take my polynomial f of low degree, and I want to imagine evaluating it at these different points along the interpolation path. And I want to, in some sense, say that the output's not going to change too drastically. Right, so what do I mean by change too drastically? So I'm going to say that one step along this path is bad if f changes its output a lot at that step. Right, so remember f is outputting some vector at each step. And if one single step, has a big change relative to f's typical norm, then we'll say this is bad. And then the result, the main stability result we'll use here is that, the probability of having no bad edge is not high probability, but it's some non-trivial probability. So what it really is that with some non-trivial probability, f's output is smooth, meaning it will never have a big jump as you go along the interpolation path. And it's sort of essential that this is only some non-trivial probability instead of actually high probability, because you can imagine some example where you just have maybe a single output and it's just a dictator function. And so, if I flip this one single bit, the output will change a lot. All right, so is this, any questions about this? So let me now explain how we're going to use this. So the second ingredient was what's called this overlap gap property. So with high probability, a random graph has no occurrence of a certain pattern, which I will draw. So S and T are going to be these independent sets in the graph. Individually, they're going to have this particular size. And then also their intersection is going to have some particular size. Okay, so this phi is just this kind of value you might remember from the optimal, from the size of opt and out. But right, this is sort of saying that there are no two independent sets that have this particular overlap pattern. Right, they both have a certain size, and they both have overlap by some exact amount. Right, so what is this kind of saying? This is in some sense saying that, the large independent sets, they're allowed to be close together, meaning they're allowed to overlap a lot, or they're allowed to sort of be far apart. They're allowed to overlap a little, but there's some intermediate overlap which is not allowed. So you can think of this as saying that the large independent sets somehow separate into clusters. And the proof of this is actually very simple. It's just a first moment method. So all you do is you compute the expected number of these bad patterns, the expected number of pairs ST that satisfy all these conditions, and you just show that this is exponentially small. So this was used by Gamarnik in Sudan, and they used this property to rule out local algorithms. Now for us, this was actually just sort of a warm-up. We actually need what's called the Ensemble OGP, which is, again, the same thing. There's this same forbidden type of set, type of pattern, but now S is allowed to be an independent set in, one of these random Ys, and T is an independent set in a possibly different one. Right, so this is an interpolation path on random graphs, right? You now think of the first one as being just drawn from G n d over n. This is one of our random inputs. And then like before, we resample one edge to go from to go along this path, right? So this is this whole collection of correlated random graphs. And this property is saying that even if I let you pick two different independent sets, one from here and one from here, that you still never see this particular pattern.
Even for pairs that are consecutive on the interpolation path?
Yeah, that's right. Even if you take both consecutive, it's still not allowed. Or if you take even both from the same. This is actually just this OGP property from the last slide.
Okay, so let me just clarify that I'm understanding properly. So even if I take S and then I resample a single edge, then the size of S is not supposed to change very much. That's
Well, it's saying that there is no there's no instance of this bad pattern. So there is no such S and T. So if I'm allowed to take S and T being both independent sets from a particular graph, we know that this bad pattern, this type of pattern never happens. But also, if you're allowed to draw S and T from any independent sets from any of these instances, it still never happens.
Even if I choose T, so S is a set in Y0 and T is a set in Y1, which is chosen to be like basically S, except for so you're saying that even that doesn't exist, like perturbing one edge will totally destroy S as an independent set.
Well, remember there's a specific overlap here. So S is not allowed to be close to T. S and T are supposed to have this exact intersection size. There's like a specific overlap that's not allowed.
Okay, I understand. Okay, thank you.
Yeah, any more questions? Okay, I know we're about out of time, but in this last slide, let me just complete the proof. So how do we use this to show that low-degree polynomials fail? So let's assume, on the contrary, that we have a function that does output large independent sets of this particular size. And let's again sample this random interpolation path where we start with a random graph and then we resample the edges one by one. And so, and what we're going to imagine doing is applying f to all of these, right? So I apply f to the first input and I get some independent set here. I apply f to the last input and get, some other independent set here. And the first fact that we need is that that the first and last independent sets have to be far apart. So this is a fact I haven't told you yet, but this can also be shown by a first moment calculation. That if you take two, right, these are two independent random graphs. And so two independent random graphs, if I take an independent set from one and an independent set from another, they can never overlap too much. So I've drawn them as sort of disjoint here. Really, they're allowed to overlap a bit. And then remember this stability property from the previous slide. So with non-trivial probability, every step along this path, the polynomial output only changes a little bit, which boils down to saying that, the independent set that I output is only allowed to change a little bit at each step. Okay, but now we can see that this contradicts the OGP property. Because if I need to get from this first set to this last set by only making small changes, there has to be some set along the way that has this forbidden overlap with the first set and contradicts the OGP. So this is how the proof goes. All right, so that's essentially the idea. So just a couple of comments to wrap up. You can improve this. So I showed the proof of some threshold, but not the optimal one. If you want to improve it really to the optimal threshold, you need to think about intersection patterns that don't just involve two sets, but involve a large number of sets. originally inspired by the work of Raman and Virag on the local algorithms. For OGP, for this other p-spin model, so the proof is essentially the same, but proving the OGP is not just a simple first moment calculation anymore. You need some kind of heavy machinery from this Parisi formula and so on. That comes from these papers. So from here, we don't currently have sort of the optimal results. We can also rule out a different algorithm called Langevin dynamics, which you can think of as kind of a continuous version of gradient descent, which also has the same sort of stability properties. Right, so really we're not just ruling out low degree polynomials, but really any algorithm that is sufficiently stable with respect to its input. And finally, I see this work as falling into sort of a broader meta question about whether we can connect these different heuristics for hardness, things like low degree, sum of squares, overlap gap property, and so on. So this is establishing a connection between the overlap gap property and the low degree polynomials. All right, so thanks, that's all. Here are just some references for more on this low degree polynomial method in all sorts of different settings. So in the detection, recovery, and optimization problems. Thanks a lot for your attention.
All right, thank you for the lovely talk, Alex. I guess now we can take some questions if people have any. Maybe while people collect their thoughts, I can sort of ask a question. So I guess a question is it the case that if you can establish, so say that I establish the overlap gap property for some other optimization problem, is it the case that you expect there to also be a black box sort of method that says that if you have the overlap gap property with such and such characteristics, then automatically that will imply low degree hardness?
Yeah, that should basically be true. Yeah, the other ingredients you need is just to show the stability of low degree polynomials in your setting. So at least if the input is sort of IID Gaussian or IID Bernoulli or probably IID just about anything, you should be able to establish that and use sort of the same kind of interpolation argument. Yeah.
I see. Okay. So, and maybe it would depend maybe on like the hypercontractivity constant or whatever for your setting.
Yeah. So that plays into the stability a little bit, but not in I mean, only in sort of a logarithmic sort of way.
Okay.
Yeah. So like here we were doing it with sparse graphs, which has yeah, and then this sparsity only boils down to some log n somewhere later. Yeah.
Nice. Okay. Thanks.
So Alex, is there a hope to understand like number of monomials as a measure of complexity for polynomials for these algorithms rather than just degree? Like, do you have, say, problems for which you know that, say, if you have a very high degree polynomial, but still computing it should be reasonable, then this still fails, or are the techniques kind of different for this?
That's a good question. I don't know how to do this in this particular setting of random optimization problems. I think we could do it in the setting of detection. If you're just thinking about something like planted clique, distinguishing between a planted clique and a random graph. In that case, I think that yes, we could prove that, yeah, that if you're allowed a limited number of monomials, that in fact, the best choice will be to take the low degree ones. But yeah, more generally, yeah, that's a good question. I don't know.
Any other questions from the audience?
So I'll pause the recording and then we can keep chatting offline.